In the previous lecture, we learned about how you can create abstraction function for a last in first out stack using the sequence class from the math models library. And in this particular lecture, we'll try to dive into a little bit further into the math models library to see how you can write some even more interesting contracts that will still satisfy the information hiding and also the single choice design principles. Let's see what the learning objectives are for this lecture. It's mainly a case study and using the birthday book example that you learned from Lab 0, which you're pretty familiar with, so we can focus more on the deeper insights into the application. Upon completing this lecture, we hope that you will understand, number one, how you can assert set equality in postcondition. We'll do one exercise together and I'll give you the solution. I'll discuss the solution as well. And number two, we'll learn about the basics of discrete math, and this one here is mainly about a review that you have to self-guide, that's mainly self-guided. So you will have, I'll give you the slides and then you have to go over details if you find it necessary. And your quiz is also going to test your knowledge on that. For example, how do you know a function, for example, a function is actually a relation, but not vice versa? So basic knowledge like that. So I don't need to waste your time by going over the lecture. You can just read the slides and then make sure you're comfortable with that, because we need those details in order to write proper contracts for your future labs and also your projects. Number three, how you can create a mathematical abstraction for a birthday book. So we learned about how you can create a mathematical abstraction using a sequence for a last in first out stack. But now how we can do that for more like a database, like a birthday book. How can we do it? And then we're going to use commands and queries from the function class, the function class from the math models. However, function is simply just a specialized version of relation, and you will be expected to actually explore further about other features that are actually available in relation but not really available in function, or they might just behave differently. That's something you would be expected to do in your lab number 2 exercise. Okay. So let's now first start with some exercise over here. Let me present to you what exercise is, and I'll suggest that you pause the video and think about how to tackle the exercise before I go over what the problem is and also what the solution should be. Okay, so now let's go on to the exercise. Let me explain to you what the problem is, and then I mean the specification what the problem is, and can tell me you can actually criticize how the current solution looks like. So what we are doing here is we are specifying a routine, especially a query called all positive values. The input is simply just an array of integer, and then the output return value is simply just another array of integer. Of course, array may or may not be empty. It's both are possible. And then the precondition over here will simply say that there should be no duplicates. So no duplicates in the input array. So this will be left as an exercise which I wouldn't discuss the solution. Okay, at this point you should really know how to write such predicates yourself. Okay, this one will be exercise for you. Okay, and then let's say the current post condition we have is just like that. We'd say basically we're using across all, so it's more like a universal quantification over the result array over here. We're saying every x in result, which is an integer, it should be strictly positive. It seems to make sense because we're saying we're going to return all the positive values. Let me just talk about one example case, right, to really show you. So for example, if you try to call as follows, if you say all positive values, okay, and then if I give you an array, let's say 2, 3, minus 1, 4, minus 2, let's say. If this is the input I give to you, what should be the return value, right? The return value should be, for example, just another array, and we'll keep the positive values only. Okay, so that will be 2, 3, and 4. So of size 3. And what the post condition is saying is, assuming that the implementation is actually correct, but can you make that assumption though, right? Let's say, assuming that the implementation is correct, so what you will get is 2 is larger than 0, 3 is larger than 0, and 4 is also larger than 0. Okay, so now this is how the post condition what they intend to do. Okay, so now I want you to pause the video and think about, is the current post condition over here sufficient to catch any incorrect implementation if it happens? So I hope you have given some thoughts into this particular post condition. Okay, the solution is, the answer is, this postcondition here is incomplete. Okay, so whenever you want to argue that a particular postcondition is incomplete or incorrect, you have to give a counter example, which means you want to demonstrate a scenario where there might be something wrong, but the postcondition cannot be triggered as a violation. That's something you would like to show. Okay, let me tell you right away. Okay, so now let's say this. First of all, we know we want to argue that this particular postcondition over here is incomplete, meaning that there will be some incorrect implementation that cannot be caught by this particular postcondition. So I will want to say it's incomplete. So if I argue this, what I'm responsible for giving to you will be a witness or like a counter example. Okay, I'll write it down here. I need to give you a witness, or I want to give you a counter example. Okay, so I'll just give you one scenario where it's actually going to fail. Let's say this. Let's say we consider the input. Let's say we are still calling the same routine query all positive values over here. Okay, let's say we still give the same input array. How about that? We still got 2, 3, -1, 4, and -2, and that's the input. And we know that the output from the previous discussion over here, this is actually correct output, right? This is correct. However, in order for you to design the postcondition, you cannot really make such a strong assumption about the implementation is always correct, and then you lose the purpose of using postcondition. So now, let's consider a wrong implementation. Let's say we talk about some wrong implementation. And the wrong implementation is going to do as follows. Let me go for extreme. What it will return is, it's going to return, let's say 1, 5, and 7. So now, this output over here has the same size as before. It contains 3 positive numbers. And now, if you evaluate this particular postcondition that I claim to be incomplete on this particular output value, which is wrong, are you going to get any postcondition violation? Apparently, no, because every x in the result, 1, 5, and 7, they are strictly larger than 0. So there will be no postcondition violation, even though the implementation is incorrect. So now you can see what the problem is, right? So now you can see, since each number in the result is strictly larger than 0, so that means no postcondition violation. No postcondition violation. And now, to make it even more explicit for you, remember what we said before. If there is something wrong, however, there is no postcondition violation, so that means your design of the postcondition is inappropriate. Okay. But the output is incorrect, which means the implementation is wrong. The output is simply incorrect, but there's no postcondition violation. So the final conclusion is the design is flawed. Okay, so hopefully you can now see how I reached that particular conclusion. That's a conclusion here, but I should really know how what's the reasoning process to actually reach that conclusion. Okay, so that's about the problem for the existing postcondition over here. It's simply not complete. So now, how can we write a complete postcondition? This is the meat for this particular exercise over here. So again, you can choose to pause the video a little bit to think about, based on your knowledge about how to use across some using logical quantifiers, how you can write a complete postcondition. You can think about it before you see my solution. Okay, so hopefully you have written down your own solution as the complete postcondition. You can compare your answer against mine. If you got any doubts about whether yours should also work, you can raise them up. Maybe in the Q&A session, or get in touch with me in person. I'll be happy to help you. Okay, let's now go over my solution here. Before I go ahead and write you the correct solution, let's first of all understand at a conceptual level what we are really trying to compare in the postcondition over here. Given that we know that there should be no duplicates from the input array A. So you can think about it's more like a set mathematically, right? There's no duplicates of the members. So what I would like to do is that I would like to start by sketching the input A over here. If you think about this is the input A over here is a set, right? I'll simply put A over here. And then the input A contains integers, which can be positive or non-positive. And there should be a particular subset over here, could be exactly equivalent to A, but that's okay. But let me say this is a subset, which means they are all the positive numbers. And the green one is something we would like to be returned actually as a result, right? And then on the other hand, we also got this particular postcondition, the output over here. You can see this is the output array, right? So let's now draw another set over here. So let me just try to be as accurate as possible. So this is just another set over here. You can think about this is a result. Of course, result shouldn't contain any duplicates, but our solution is going to catch that if you do contain the duplicates. So what we really want to do in the postcondition over here is to really make sure that this set over here is equivalent to this set over here. We want to say these two are matching. So they're completely equivalent to each other, right? So now if you try to recall in 1090, how do you prove that two sets? Let me just make it even a little bit more closer to how you learn in 1090. Let's say this is a set called S, and this is a set called T. How do you prove that over here? Let me write it down here. How do you prove that S is equivalent to T, right? We know pretty well it's equivalent to, for every X, such that X is a member of S implies X is a member of T, and also X is a member of T implies X is a member of S. Okay, that's a complete definition over here. But equivalently, you will know that this part over here is telling you that S is a subset of T. And also this part over here is telling you that T is a subset of S. If you combine these two things together, you know that the equality should hold, right? That's what you learned from 1090. Just a very quick review, okay? So now all we're going to do is we want to specify this as one postcondition. We want to specify this as the other postcondition. Basically, we want to specify two subsets relation. Okay, let me use a different color here to emphasize that. We want to do number one, subset, and number two, just another subset. Okay, so now let's see how we can do it. Okay, so I'm going to write it down separately. Let's say the first one, we want to assert that this set over here is a subset of that, and the second one is going to be this set here is a subset of this set over here. Let's do that separately. Let's do that. Let's do the first one here. So let me use green over here. Let's say all positive in A also in result. So what I'm saying, I'm trying to make the tag a little bit wordy, but it's as informative as possible. I'm saying every element in here should be also an element over here. So I'm proving that S is a subset of T, right? So now how do we write it? I'll write that one here. So you can say maybe across. So there should be universal quantification. So we can say across over here. Let's say across the elements of A. So across A, we can across an array. We learned about it in lab 0. Is, let's say, X. Okay. And then it's going to be universal quantification. I want to say those positive numbers. So we should say that over here, that should be X that we talk about. X larger than 0. And then every member either larger than 0 or less than or equal to 0. So you cannot use conjunction over here. You want to say if they are negative, we don't care. Right? So that means logical implication would be the appropriate one to go. Okay, so I would say implies over here result, right? It's also a member of the result. Result has over here, and we know that you can assume that the result the object comparison is actually true. Okay, but since we talk about integer, so it doesn't really matter. Result.has over x over here. Okay. Okay, so that's the first post condition we can have. So this will effectively assert that S is a subset of T. Okay, so that's the first one. Okay, hopefully you're fine. Okay, let me just make it a little bit smaller here so I can put both post condition on the same page, so you can also compare and contrast. Okay, let me just make it a little bit smaller over here. Okay, so that's the first one. Okay, what about the second one? The second one here, we want to say every member of the result is also a positive number in A. What we'll put it another way. You want to say every member in the result, number one is positive, number two is also a member of A. So it's effectively saying the same thing. So it's pretty easy, but I'll just write it for you. It's a complete exercise solution. But of course, once you get the idea, you should really, I'll make a recap at the end. Okay, so now how do we do that? Let's say, let me use maybe another color here. How about just pink? Okay, so now we want to say all positive. Okay, how about this? All number in result positive, and they're also in A. Okay, again, it's a little bit wordy, but I want to be as informative as possible. Okay, so that's just a tag name. So I'm saying all the number in the result, number one, they should be positive, and number two, they should also be a member of A. Okay, so what I will do is I'm going to say across the result, right? I'm gonna you can see the target of going across is different. In the previous one, I'm crossing A. Here I'm crossing the result, right? It's different. Crossing the result is, I'll also say X over here. It's just a dummy variable, so that's fine. So now I'm going to say all over here. So I'm going to say for every one of them, number one, it should be strictly positive. So now I want to say every one of them. So there should be no exception. So that's why implication would not be the way to go. I want to say conjunction. For example, if your result actually contain, for example, let's say -1, for example, in that case, it should be considered as a post-condition violation right away, right? That's why I need to use conjunction here. Okay, let me go back here. I want to say X is larger than 0, and so there's a conjunction here, and also it should be a member of A. A dot has X. So this one here is now, let me circle that. This one over here is now the symmetric one. So this one here essentially proves that T is a subset of S, right? So now after these two post conditions, we can essentially asserting that these two sets are completely equivalent. This set over here and this set over here. Okay, that will be about the exercise I would like to talk about, but there are many things you want to pick up also to reflect on yourself. Let me give you some guidance over here. So this exercise here presents a very general problem that you can solve for your future labs or your projects. Whenever you're talking about your return value over here being a set, conceptually, right? Even though it's a linear data structure over here, but if you can somehow assume that there will be no duplicates, or maybe you can actually restrict its range to be some subset without any duplicates. Either way, whenever you talk about the result value being a collection, you can definitely apply this pattern here. You want to argue about what does this collection really contain. Okay, so now you can actually think about conceptually, for example, this might be the set you believe should be equivalent to the result collection over here. So that's why you can say, number one, it should be a subset this way, and also it should be a subset this way. You should need two post conditions as illustrated to you. Okay, so now, in order for you to move on to the next part, in which case we're going to start talking about the birthday book application applying this particular insight. So you may actually want to review very quickly why the original post condition was incomplete, and also why we need these two post conditions over here to make it complete. Okay, think about it, and then if you got your own solution which you believe is also correct, you can raise them up maybe in the Q&A session, or you can get in touch with me in person. Okay,